Okay, in this problem, we have people taking or not taking ginkgo supplements, which are advertised to improve memory. We have two separate groups, ginkgo and a placebo. What I would recommend in these, and we're talking about means, is that anytime you work a problem on these, that this be the first thing you do, that you make a table similar to what I have here. That won't always be given like this in a problem, but you should do it anyway. So it said we had 24 participants. We have 24 here. It said we had a mean of, well, actually in this case, they're already in here. So we have the means and everything in this table. Once you have in the table here, we want to know if we have a pooled or unpooled variance. So we look at the variances. Make sure you're not looking at the standard deviations. We look at these variances, and we look to see whether or not one of these is more than twice the other. And since 0.36, the higher, is not more than twice the other, that means we can pool. They are close enough to be able to pool the variances. While I'm right here, let me also make a point, and that is that when we do this problem on our calculator, that it's going to have a place to put in standard deviations, not variances. So on your calculator, make sure you enter standard deviations, but when you're making the decision as to whether pool or not, make sure you look at the variances. So the first thing we'll do is a 90% confidence interval. So let me go ahead and say since it's pooled, the degrees of freedom is just NA plus NB minus 2, or 24 plus 24 minus 2 is equal to 46. So back to the confidence interval. It's going to be the statistic x bar A minus x bar B plus or minus a t-value that's based on 46 degrees of freedom and 90% confidence times the standard error, which for the pooled, the standard error is, this is the longer of the two formulas, s squared A NA minus 1 plus s squared B times NB minus 1 over NA plus NB minus 2 times the square root of 1 over NA plus 1 over NB. So we have 5.7 minus 5.5. I'm moving too fast, just pause for a second. Plus or minus, now we need the t-table, and we're looking for 90% confidence and 46 degrees of freedom. So 90% is the first column here, and 46, we're going to have to move down a little bit. And so 46, that's going to be 1.679 right here. So that's 1.679. And you could calculate all of this and just have the standard error, but I'm just going to put it in and calculate everything at once. The square root of 0.36, that's the variance of the first group, times 23, that's n minus 1, plus 0.25 times 23, again that's just 24 minus 1, divided by 24 plus 24 minus 2, all of that multiplied by 1 over 24 plus 1 over 24. So everything on this right-hand side is called margin of error. I'll call that MOE. And when you see things reported in the news, they'll often give you some statistic and a margin of error. When we compute margin of error, remember it's going to be a confidence coefficient times the standard error. So all of that is the standard error. Well, when you calculate all of this, this is going to be minus 0.068 to 0.468. You should verify that on your calculator, the stat function, stat, tests, 2-sample t interval, and enter in the information from the problem, making sure that you use standard deviations, not variances. In fact, when I ask you to work a problem, I am going to ask for the formula. I am going to ask for explicit entry of numbers into the formula. And then I'm going to ask for a solution. Well, that you have to write out. That you have to write out. You could just get this part from the stat function on your calculator. Or, of course, you can enter all the numbers in and do the calculation. Up to you. So let's interpret this interval. We're looking at the difference between two means. Well, if the interval has 0 in it, 0 means there's no difference. Since 0 is in the interval, and we'll always look to see whether 0 is in the interval, 0 is in the interval. Therefore, there might not be a difference between population means. That is, mu A could equal to mu B. Of course, we know there is a difference between sample means. We calculated those. It's 5, 7, and 5, 5. But that could be so close, in fact, it is close enough that we would say that could have, this difference between means, between 5, 7 and 5, 5, which is just 0.2, that could have occurred by chance. That doesn't mean it did occur by chance. That's why we say might. It might, there might not be a difference. Obviously, there could be a difference. We just can't say that there is. We don't have enough evidence to conclude that there is a difference. 0 is in the interval. Okay, let's do the critical value approach. And in this case, we're looking at improved memory. So we want to know if the mean, I'll call this group A and group B, if the mean for group A is greater than mu B. Of course, HO is going to be that the two population means are equal. And you'll see, especially when we get to the p-value approach, well, even here, when we do our calculation, our formula, we could rewrite this mu A equal to mu B as mu A minus mu B is equal to 0. Of course, if the difference is 0, they're equal. We're going to reject HO if t-test is greater than some value, and if you look up 0.5 and a one-tailed test, you're going to be back exactly where we were with the confidence interval, and this is going to be 1.679. And the t-test, if I say write the formula or show all your work, you will have the statistic minus the hypothesized parameter, which this part is always going to be 0, or at least for this class. We could say, do they differ by at least 10? But for this class, and for most applications, we'll just use 0 there, divided by the standard error. That same thing we had a minute ago, S squared A NA minus 1 plus s squared b and b minus 1 and that all comes out to be 1.25, which is, I'll put here 1.25 is not greater than 1.679. So we fail to reject HO. Conclude, as we did before, mu A might not equal mu B, which means the ginkgo, putting this back into the problem, might not be effective. The improvement that we saw that went from 5.5 to 5.7 could have just been a chance happening. You need to pause and get all that down. I'm going to move on to the p-value approach. Just to repeat, we had HO mu A minus mu B is equal to 0. HR mu A greater than mu B. Of course, I could have put mu A minus mu B greater than 0. You'll see when we do this part that it really is convenient to have the null hypothesis stated in this way rather than mu A equal to mu B. We're going to reject HO if the p-value is less than 0.05, and we'll have to use our calculators to get the p-value on this. So stat, test, 2samp t-test, enter your information, making sure you put standard deviation, not variance. And when you do that, you should arrive at a p-value of 0.108, which is not less than 0.05. So now the same thing as before. Fail to reject HO. Mu A might not equal to mu B. The ginkgo might not be effective in improving memory. While I'm here, let me also go ahead and remark that we have the same rules for deciding whether or not we have a bell-shaped sampling distribution, but you have to look for the smallest n. Both of these are 24, so you just need to look at 24. So 24 is greater than 15. Skew is okay. However, 24 is not less than 40, so outliers are not okay, or that is to say they would invalidate this process. You have to have a large enough sample in order to guarantee that the sampling distribution will be a bell curve. It's not exactly with a t-test exactly a bell curve. It's something like that. I mean, I'll just draw quickly here kind of the difference. If this were a bell curve as we would have with the z distribution, a t distribution would just be slightly flatter. At small sample sizes, it might look like that. So instead of rejecting HO right here, you might have to be out here in the t distribution. Think about it. You have less information. You don't know the population standard deviation. It has to be estimated. Therefore, there's a little bit more uncertainty, and you have to go a little further out before you reject HO. Well, if you take larger sample sizes, well, it's not a very good picture there, but they will get closer and closer to the normal distribution until you get to infinity and or even when you get to infinity, they'll be exactly equal. But the larger the size of the sample, the more closely t approximates the z distribution. Okay, in problem 2, instead of already having a table, the information is all embedded in the problem. So the first thing we'll want to start off with is making a table that has everything in it. What I'm going to do is make it this way: A and B in x bar, s, and s squared. In this case, n is 31 for both groups. For group A, and you can put these in, you can call A and B whichever one you want to. Since the mean for A is greater, I'm going to let this be the older and this the younger. And we had 20 and 14. And the standard deviation for the older was 7.3 and 5.1 here. We need to square those to get the variances, and we get 53.29 and 26.1. 53.29 is more than twice 26.1. So this is greater than twice what you have over there. Therefore, it's so far apart, they're not close enough for us to pool, so we will use the unpooled variance, and we'll also need degrees of freedom. The degrees of freedom for the unpooled test, there is a formula for it. It's called a Sater-Waite approximation, and you can look that up. I think for our purposes in this class, I think it's just better if we just get this straight from the calculator. And so what you'll want to do is go to your calculator and put in the information for the problem, stat, test, 2-samp t-test, or interval. It doesn't make any difference which one you put right here. And put in the numbers from the problem. And make sure you put no when you get down to the pooled, because we've said unpooled. And hit calculate. And you will see, let's go ahead and write down some check figures here. We have t is equal to 3.75. So when we do get around to doing the critical value approach, we should expect a t of 3.75. When we get to the p-value, we'll get 4.33 times 10 to the minus 4th, or 0.00043. And so, and also there it'll have degrees of freedom is 53.65. Well, just get rid of the decimal part. Always round this down, so our degrees of freedom will be 53. I think on this problem I'm going to start with the p-value approach, because I want to make sure, I don't think I did in the previous problem, I did do the p-value approach, but we didn't draw the sampling distribution. I want to make sure we have something right away where we have done that. So I'm going to do the p-value approach. We're looking at whether or not there's a difference. So HO and HR, mu A equal to mu B, or mu A minus mu B is equal to 0. Mu A not equal to mu B. In other words, this is going to be a two-tailed test. We're going to reject HO if the p-value is less than whatever our level of significance is, and that's going to be 0.005 in this case. And we have the p-value from our calculator. Whenever we have anything using the t-table, we will just use our calculator to obtain p-values. 0.00043. That is less than 0.05, so we will reject HO and conclude mu A not equal to mu B. Be careful, you can't conclude greater than. We have to stick with the hypotheses that we had to start with. So all we can say is that there is a difference in the vocabularies of older and younger adults. Let me just draw this out, the sampling distribution for this. Make sure you label the axis, x bar A minus x bar B. The center is going to be mu A minus mu B is equal to 0. That's one advantage of stating the null hypothesis in this way, mu A minus mu B is equal to 0. You know what number to put on here. In fact, it'll always be 0. I'm just going to put that we have some standard error, and I'm going to use the shorthand S of the x bar A minus x bar B. All this is a subscript that tells you what the sampling distribution is. And we observed a difference of 20 to 14. We observed a difference of 6. So we have p-value down here. But let's remember that our HA was mu A not equal to mu B, and it was a two-tailed test. That means we have p-value in this side as well. And we know this distance is 6. So this distance also will be 6, and this is going to be minus 6 down here. So when we want to state this, and I'll ask you to state the p-value if then, or I might say state it conditionally, we would say if mu A minus mu B is equal to 0. You could just say if mu A is equal to mu B. That's just a matter of preference. Either one of those will do. If HO is true. If HO is true, then there is a p-value chance, a 0.00043 chance. And when I used my calculator, I used not equal to in the for the alternative hypothesis near the bottom of the page. So it's already done the doubling. So this is the entire p-value. So if HO is true, then there is a p-value chance of observing what we have shaded in the tails. So I'm going to put this way, one of the following. A x bar A minus x bar B greater than 6. That's the easy one. It's easier to see and think about. Or, again, basing this on the hypothesis that we had, which was two-tailed, or getting x bar A minus x bar B less than minus 6. So in this area out here. I'm going to move on. If you need to pause, go ahead and do so. So all of that's the p-value and then drawing the sampling distribution. Let's go ahead and do the critical value approach now. So our hypotheses are going to be the same. HO mu A equal to mu B, HA, or HR, whatever you want to call it, H1, mu A not equal to mu B. And of course, again, I'm going to go ahead and write that as mu A minus mu B equal to 0. We're going to reject HO if t-test is greater than some value or less than minus that same value. Remember, we had degrees of freedom was 53. Used our calculator to obtain that. So we have 0.005 level of significance. I'm going to go ahead and note for the next part of the problem that's 99% confidence. That is the last row on the right. Scroll up there and verify that. So 99%. This is a two-tailed test. Revise that problem. I'll have it revised by the time I put it out to make that 0.01, not 0.005 for the p-value. And so we had 53 degrees of freedom. That'll be 2.672. 2.672. So let me first of all go back and just say that just to make everything stay consistent, wouldn't be anything wrong with leaving the problem as is, but I think there's a little bit of a nicety to leave things consistent. 0.01 on a two-tailed test goes with and is going to give you the same critical value as a 99% confidence interval. So let's change that to 0.01. And so then we would have 0.01 here and here. Again, either way is okay. I'm just doing that to make it so we have the same critical value as we do for our confidence level value. Okay, so back down here. We had said that we would have 2.672 there. And so now we will compute the t-test as the statistic, x bar A minus x bar B, minus the hypothesized parameter. Hopefully you're getting a little bit tired of hearing me say that, and that you know it now. That's why you're tired of it. You wouldn't think I would need to keep repeating it, but I will. Divided by the standard error, which for the unpooled is s squared A over NA plus s squared B over NB. Put all this in, we still have 20 minus 14 minus 0. You could just write 6 there. It might be better for you to think of that as a difference of 6. That's what our sampling distribution is, a distribution of the difference between means. So we have here now the square root of, make sure you get the variance here, 53.29, so 5. I'm sorry, that's nothing there. divided by 24 plus 26.01 divided by 24. And that all comes out to be 3.75. Again, you should be able to calculate it this way, but you can always go and use the stat function on your calculator either to verify or actually just to do the calculation for you. I will again ask for the formula. I will ask for explicit entry. You can't do those on your calculator, but I'll also ask for the solution, of course. You can get that from your stat calculator if you would like, rather than calculating all of this out by punching all the numbers in your calculator and with the formula and everything. Either way, that's greater than 2.672, so we reject HO and conclude, as we did before, that mu A is not equal to mu B. The ginkgo is, we can't be confident, we can't be sure. Actually, I'm sorry, thinking back to the wrong problem. Ginkgo. I need some ginkgo to improve my memory, I guess. We're not talking about ginkgo anymore, we're talking about vocabulary. So the vocabulary is difference. The average difference is the average difference in vocabulary is different for older and younger adults. Okay, good. I was going to go back and make sure I didn't put ginkgo on the other part as well. Okay, so let's do the 99% confidence interval. That will be the statistic, x bar A minus x bar B, plus or minus confidence coefficient T, times the standard error. Again, I know I keep repeating this. That's the statistic plus or minus a confidence coefficient times the standard error. Been like that for a couple of days, and it'll be like that exactly in the next couple of lectures as well. And I think everything, all the confidence intervals on the next exam will follow this pattern. We have a couple of different choices that we haven't gotten to yet, but that's the pattern. So 20 minus 14, or just 6, plus or minus 2.672 times 53.29, 24, 26.01, 24, that's 1.73 to 10.27. If you need to pause, please do so. We want to know if there's a difference. What we need to do is look to see, does the interval include 0? This interval does not include 0. Therefore, we conclude mu A not equal to mu B. There is a difference in vocabulary. We are confident of that. The results that we observed be very unlikely if there were a difference. In fact, we calculated how likely a little bit ago, 0.00043. Not that it couldn't occur, you can't be certain with statistics, but it would be highly unlikely for us to get a difference of 6, given and everything else we have. A difference that large is not impossible, but highly unlikely. Okay, given the time that we had in class today, for the next two, just going to give sort of an overview of what to do. So first of all, when you're looking at these problems and you have 2 columns or 2 rows, however it's presented, of numbers, and you will have some of these, the choice that you need to make, and this and the next problem, I'll give you examples here, and you'll see more in your homework and in other places, is when we look at one row here, is this person the same person as this person? Well, unless you observed somebody at one time in their life and waited 20 years and observed them again, these are different people. Therefore, we're talking about 2 groups, Group A, Group B. These are 2 independent groups. Therefore, we're talking about the difference between means and we're going to get x bar A minus x bar B plus or minus. Just want to get us into the start of that. I will go ahead and say in this one that I will sometimes, frequently in fact, permit you to let your calculator do all of the calculations. And so what you would want to do is put these numbers in a list. You could put them in list 1. Put these numbers in a list. Let's say we did that with L2. And then you would do stat, tests, let's say we're doing the confidence interval. You would do stat, tests, and then I believe that that's going to be option 10 or 0. It's got a 0 there, but let's say it's 10. 2 snap t interval. Now this assumes that we already have the numbers in list 1 and 2. Which I do from earlier. So I'm going to put that in. I'm going to do stat, calc, 2samp t-test, and I'm inputting data. So at the top, change your input to data, and then refer to the list numbers that you have in the problem. I had mine in list 1 and list 2, so for list 1 I'll put L1, second 1. For list 2 I'll put L2, which is second 2. Don't change the frequencies, go down to the confidence level, and we're using 99, so make sure of that. Now we don't know yet, unless you had already computed the standard deviations and variances, whether or not we should pool. So I'm going to select no. You got to pick one of them, 50-50. And now I'm just going to look down at those standard deviations. It says SX1, but that's SA, that's 8.68, and SB is equal to 8.54. Well, it's obvious, but let's go ahead and do it the right way. So S squared A is going to be 8.68 squared, 75.34, and S squared B, the variance, is going to be 8.54 squared. and that's 72.93. Well, neither of those is more than twice the other. Therefore, I should have answered yes. This is going to be pooled. So I'm going to go back now and do stat tests, back down to the 2-sample t interval, and everything else is the same except for make sure you say yes to pooled. And my interval would be 5.31 to 27.49. 5.3123, 27.488 if you want to carry that all the way out. That interval does not include 0. Therefore, and you'll see this is a one-tailed test, but there is a difference, and it's going to turn out that the scores were higher for older. I call this A and this B, which is the same thing as saying they're lower for young. And it's just looking at if there are differences, so it's going to be a two-tailed test anyway. Okay. From there on, it's just the same whether you use your calculator or not. And of course, your calculator also had the means there. So it's just the same problem we did a second ago. I think number 2 was actually the one that was pooled. Actually, it might have been number 1. Number 1 was pooled. But that's really not what, at this point, I want to focus on. I want to focus on that was 2 separate groups, older adults and younger adults. Therefore, we did the difference between means. We have 2 independent groups, as opposed to the kind of problem we did yesterday, where we're looking at this anti-hunger pill, and we have 10 people. We could number them 1 down to 10. So there's just 10 people, and this first observation is for one person. This is just one person here, not 2 separate people. That means that we're going to have a matched pairs t-test. So it's saying calculate the sample statistics. I'm not going to do all of this right now, but just to get you kind of going, this will be like what we had yesterday. For the first person, there was a difference of 2. For the next one, 4. For the next one, 5, and so on. Then, next we have 10 people. We really only have one measure, and that is how much they differed. So we can actually, from this point forth in the problem, just forget the before and after, just focus on these differences. Then you can compute x bar of these, and you can compute the sample standard deviation of those, just like we did on the first test. Not going to work it out here, but I'll go ahead and repeat the formulas for you. And then now you have what you need to do, a one sample t-test. One sample. We had the before and the after, but there are only 10 people here, 2 measures on each, as opposed to the previous problem where the people we had, I think it was 12 older adults, 12 younger adults, 2 separate groups. Then you can do a t-interval, a t-test, depending on which way we subtract. If we're talking about reduced ratings, we want to know if the after is lower, which is the same thing as saying that the before is after. So if I did before minus after, then my alternative hypothesis is going to be mu greater than 0. Had I subtracted in the other direction, after minus before, then that would be mu less than 0. Remember also that you should be able to do this one on your calculator. Just a note of review that you would be putting those into, let's say, list 1 and list 2. So if those were in L1 and L2, then what you need is to go to on your calculator the list of L3, highlight the L3, then do second 1, which is going to give you list 1, minus second 2, which is going to give you L2. So when you have this highlighted, you can write formulas down in the bar at the bottom. And then when you push enter, it's going to put these numbers in it, the 2, 4, 5, and so on. And then you can run a t-test on those numbers. If you did this on your calculator, you would do stat, test, t-test, just one sample. And then if you wanted to put in data, you would refer to L3 for your data, not L1 and 2. Once we have the L3, once we have the X's, the other two, the before and after, the L1 and the L2 are out of the pool, so to say. Okay, that's all I have for today. And we'll see, or I guess not see, if you're not seeing me, later.